We're going to continue looking at Chapter 13 by looking at rates and regioselectivity in electrophilic aromatic substitutions. The substituents that you're putting on, of course, will go on at certain rates depending on its regioselectivity. So we've got a chart that we're going to use to determine how strongly activating or deactivating a particular substituent is. Activating substances increase the rate at which your electrophilic aromatic substitutions occur. Deactivating, of course, slow it down. So if we look at this chart, if you look at the top of this chart, and this has been posted for you on Blackboard, you can see that this very strongly activating substances are going to have your nitrogen group, so your amines, your amino groups, and of course your OH group for your alcohol. These are all ortho-para directing. Since ortho and para are two different positions on the benzene ring, then you can actually make two products when you're doing this particular mechanism. The next one, you can see that these have a lot of carbonyl carbons in them, but they are specific ones that either have a nitrogen or an oxygen attached to them. Your R that's here represents your alkyl group, so that could be a ring, it could be a straight chain, it could be a branch chain. This is your arene or your benzene ring type molecule. This is your vinyl groups or your ones that have the double bond or grouping. Again, all of these are ortho-para directors. And when you get down here to your halogens, they are deactivating, but they are still going to be ortho-para directors. So you can still form two products, one in the ortho position, one in the para position. As you move on down, you can see things like this one, your group that is found in your aldehydes, your ketones, your acids, your esters, your acyl chlorides, and so forth. When you get down here, your cyanides and so forth, these are all going to be deactivating, strongly deactivating, with these being the most strongly deactivating. And these are meta-directing, so these will only form the one product in the meta position on the benzene ring. So we're going to be looking at reactions throughout the rest of this chapter. When you're just putting on one functional group, it's not going to really affect where it goes, but when you have a second functional group to add, then whatever your first functional group is will direct where that second group will go, and that's one of the things we will focus on. So in this particular case, if you're looking at this particular reaction, if we start off with toluene, which already has a methyl group, if we go back and look at our chart on the R groups, remember that R group was an ortho-para directing structure, so this is going to direct our NO2 group to attach in the ortho position and also in the para position. So those are our two highest quantities that are going to form. Meta is very, very low, so we typically don't even write that one on there. If you look at this one, on the other hand, this group is a strongly deactivating substance, so it's going to attach in the meta position. So even though you can put it in the ortho and para, you can see the very low percentages, the meta position gives us this highest quantity. So the next thing I want to look at, just real briefly, are what I refer to as partial rate factors. These are experimentally determined reaction rates that can be used to determine what percent of substances will be ortho, para, or meta. And also, you can compare two substances together to see which one and how much faster something will undergo a particular process. These are two examples that you'll see. So here you have your toluene. With this group, remember, it's an ortho-para director, so our ortho position and our para positions have fairly high numbers in comparison to our meta. Here we have a tertiary butyl benzene. This group is very, very large, so even though it's an ortho-para director, these ortho positions are very crowded out by this large molecule up here, or this large structure up here. So therefore the numbers are fairly small, so the pair position is the ideal place to attach something here. If you look at benzene by itself, benzene is just ones all the way around because all of its hydrogens are equal. So you can attach it any one of those at the same rate. So let's look at an example of a problem that you might see using partial rate factors. Now these are all based on nitration, but you could have them for other reactions as well. So that's what all of these numbers have been derived from experimentally. Here we have, it says, how much faster will nitration occur between benzene and toluene? So the first thing we need to do is determine our total partial rate factors for each of our substances. Of course, for benzene, it's pretty easy. We have 6 ones, so its total is going to be 6 times 1 or 6. For our toluene, you're going to have your 42 times 2. You're going to have your 2.5 times 2. And then you'll have your 58. So you should get 147. The next thing you want to do, obviously you can see toluene has a much higher partial rate factor than the benzene, so it's going to be carrying out nitration faster, and to determine how much faster, you simply put their totals, the highest total on the top, lower total on the bottom, and then calculate out. So this 24.5 basically tells me that toluene is going to undergo nitration 24.5 times faster than the benzene will. So take a minute and see if you can try to figure out which will be faster and how much between benzene and tertiary butyl benzene. Here's your tertiary butyl group. So if you need to stop the video and you want to try to see how this works out, that would be good. And then I will show you the process in just a minute. All right, so for a T-butyl benzene, if you go back up here, you have the 4.5 times 2. You have the 3 times 2. And then you have the 75, which is in the pair position. That gives us a total of 90. So if I take my 90 and divide it by the 6, then that's going to tell me how much faster that, in this case, the tertiary butyl benzene occurred. So it should be 15 times faster than nitration would occur in benzene itself. Now another thing you can do with this is you can predict what % of your products are going to be ortho, para, and meta. If you have an ortho para director, then of course those are going to be the higher numbers and you expect their percentages to be higher. And then of course the meta would be lower and vice versa if it's a deactivating substance. So let's look at tertiary butyl benzene for an example. So if I go back and look at my tertiary butyl benzene here, in my ortho position I have the 4.5. So I'd have 2 4.5s, which would give me a total of 9. And then I want to divide that by the total overall partial rate factor. So in tertiary butyl benzene it was 90. So, and then of course multiply by 100 to make it a percentage. So 10% of my products in nitration I would expect to be ortho. If I do para, then the para position has the 58, so it's a much higher number. So I'd have the 58 divided by the 90, multiplied by 100, and so my quantity of para, I'm sorry, it should be 75. I was looking at toluene. If I'm looking at 75, then if I look at 75 divided by 90 times 100, this is going to tell me that 83.3% of the nitrations in tertiary butylbenzene are going to be in the para position, which makes sense because, of course, you can't put in too many in that ortho because of that big tertiary butyl group at the top. And then for the meta, our meta position was 3 times 2, or 6. So 6 divided by our 90, then times 100, gives us 6.7. So only 6.7% would be in the meta position. So take a minute and see if you can do the same for toluene. Figure out what percentage of nitration products will be ortho, what will be para, and what will be meta. We already know that overall toluene is 147, so that's going to be our denominator for each of these. So all we have to do now is look at our toluene in our different positions. So you can see here that we have 42 in our ortho position. So if I'm doing ortho, it's going to be 42 times 2, or 84, divided by my 147 times 100. That's going to tell me that 57.4% of my nitrations and toluene are going to be in the ortho position. For the para position, it's 58. So it would be 58 divided by the 147 times 100. That's going to be 39.4. Before 6%, I guess. About 5 here. And then our meta position was our 2.5 times 2, or 5, and that's going to be, of course, divided by 147 times 100, so that value is around 3.4. So you should be able to do problems like this, and I know you have one book problem you're supposed to be trying to do on this order as well.